Okay, we're going to go ahead and get started. So it's my pleasure. It's my pleasure to introduce Dr. David Andersson. So Dr. David Andersson received his PhD in material science and engineering from the Royal Institute of Technology in Stockholm, Sweden. He joined Los Alamos National Laboratory as a LANL Seaborg postdoc in 2007. In 2009, he was converted to staff, and he is now the deputy group leader of MST8, that's the Material Science in Radiation and Dynamics Extremes group at the Los Alamos National Laboratory. Since 2004, he's also the National Technical Director of NEAMS. That's the Nuclear Energy Advanced Modeling and Simulation Program. This is a U.S. Department of Energy Office of Nuclear Energy program that is focused on developing advanced modeling and simulation tools to accelerate the deployment of advanced nuclear energy technologies. Before becoming the NEAMS National Technical Director, he was also the Deputy National Technical Director for the Advanced Materials and Manufacturing Technologies, which is a DOE program. And in 2023, Dr. Andersson was awarded the American Nuclear Society Mishima Award, which for advancing our understanding of nuclear fuel performance through fundamental studies of defect properties and their integration in performance models. And today, he will give us an overview of the DOE NEAMS program and a review of how multi-scale simulations can inform nuclear fuel performance models. Thank you for being here with us.
Thank you very much for that introduction. First, I'm really happy to be here in Wyoming and to see so many people in the room, students, and all the way up to professors. Great. I have probably what is way too many slides. I'm going to try to cover the two jobs that Laura mentioned. So probably the job I spend most time on is to lead what's called the NEAMS program, Nuclear Energy Advanced Modeling and Simulation. As said, that's a DOE, Office of Nuclear Energy funded program to develop advanced methods and computer simulation tools for reactors. The other part of my job is now a management job. We'll ignore that part of it. It's not so much interesting to say about that. But my career I spent doing various simulations for nuclear materials and nuclear fuels. I do want to talk a little bit about lessons learned on that and maybe point to a few important topics for the future. So with that, I'm going to get going. I will leave some time for questions at the end, but if someone has a burning question while I'm speaking, don't be shy. Raise your hand or just shout at me. As will be obvious, I'm not the only person doing all the work that I'll present here. Rather, it's a fairly large team over a long period of time that I've contributed to various aspects of this. I'm not going to go through all the people here, but I do want to thank my colleagues at Los Alamos and INL. We have worked for many years, Idaho National Lab and Los Alamos National Lab. We have worked for many years on problems related to nuclear fuels and nuclear materials. Maybe I should start actually by, I said I was from Los Alamos National Lab. For those of you, many of you probably know it from the Oppenheimer movie, but it's about, if you drive, it's probably 10-ish hours straight south from here. You end up in northern New Mexico, close to Santa Fe, about 45 minutes outside of Santa Fe, which is the capital of New Mexico. It is a deserty climate, but it's a fairly high elevation, 7,000 feet, so we do get snow and we do have skiing. Not as cold as here, but also not as warm as Phoenix. That's somewhere in the middle. It's a pretty nice place. Like here, you have a lot of outdoorsy activities that you can engage in. The lab has been there since the early 40s with the start of the Manhattan Project. The research and development related to what was done in the Manhattan Project is still the core mission of the laboratory, but the lab does a lot of research beyond that, including for energy applications like nuclear energy. So with that, let me jump into what the NEAMS program does. So the preface of the NEAMS program is summarized in the first bullet there. So I'll read it to you for clarity. Predictive modeling and simulation enable innovation in the development, licensing, deployment, and operation of nuclear reactors by delivering high fidelity results and increasing the value of often limited experimental data. So there are a couple of important points in that statement. So, we need more energy to power data centers and AI application, and as well as other industrial applications and residential needs. If we're going to get nuclear reactors or new nuclear reactors on the grid, we need to cover everything I said there. They need to be developed. They also need to be licensed by the Nuclear Regulatory Commission. They need to be safe. They need to be able to be built and deployed in a way on a schedule that's as fast as possible while remaining safe. And once we have built them, we need to be able to operate them efficiently. A good example of that is the current fleet of light water reactors, many of them built during the 70s and 80s. They were efficient from the start, and they were used to fuel well, and they didn't have too much downtime. But if you look at the improvement that the light water reactor industry went through over the last, like 30 or 40 years, they have made tremendous improvement. And the capacity factor, I think that's the right term, so the amount of time that the reactors are up and actually producing energy is very, very high. The number of failures of fuel, failure of a fuel doesn't mean there's a safety problem. It just means you need to interrupt your operations. It's really high, really efficient, and to get the advanced reactors that are today being designed, they will first be deployed and run, and then there will be a lot of operational things that will be addressed, probably in a quicker manner than for the light water reactor industry. Nevertheless, optimizing the operations is a very important part of taking those initial designs to something that is optimized and can produce as much electricity and, by extension, make money for the people investing in it. All right, so that's an important perspective. The U.S. Department of Energy, Office of Nuclear Energy, you can go to the website and see what their goals are. There's a couple of them. Some of the key ones is make sure that the current fleet of reactors keep functioning and providing electricity to the country, and also deploying new reactors. What NEAMS does for modeling and simulation helps with those goals. I actually forgot the second point I was going to make up there is that in the nuclear field, collecting data on irradiations, it's expensive, it's hard. You need to put materials in a reactor. It takes time. Once you take the material out, it might be hot. Hot meaning being very radioactive. You may need to wait for a number of years before you can test it. Well, it's complicated. So if you can model some of those processes and work together with the experiments, you can make the most out of those very expensive data points that you collect. That's a really important part for advanced modeling and simulation. And there is a third one that I don't capture up there, and that is connection to today's development of AI techniques. In order to train an AI model, you need lots of data. If you need to wait that long to collect that data, you're not going to have lots of data. Modeling and simulation can provide synthetic data that you can help train AI model and machine learning models. That's a field that's very quickly emerging. You're going to hear much more about that, but probably not from me. That will be another speaker. So what do we do to sort of achieve the vision that we state up there for advanced modeling and simulation? So this program develops tools, simulation tools, computer codes. Show you a little bit more about that. You can also go to a website, neams.inl.gov, if you want to learn more about the details. And those codes, they cover the key physics that goes on in a nuclear reactor. In order to call yourself advanced modeling and simulation, you also need to spend time making sure you connect to new development in the advanced modeling and simulation community. For us today, that means multi-scale simulations is not new, but it continues to be a foundational piece and continues to evolve both for materials and for fluids. You need to connect to AI ML like so many other fields and a few more topics. developing these tools and connecting to advanced methods on its own is not sufficient. We need users. We need people to be able to apply our tools to make an impact on what they are doing. So that means we have to provide some baseline support, and we need to provide some validation and verification to convince users that our tools provide the right answer for the right cases. And the last bullet is perhaps the most important one, because we're a modeling and simulation program. We want to contribute to building reactors. We're not going to build any reactors, but just running computer simulations. So we need to work with the full breadth of stakeholders, including universities such as yours here and industry, to help the whole community move forward on these topics. Let me provide a little bit of overview of what we do in the program. So I said that we cover all the relevant physics that goes on in a nuclear reactor, and I'm not sure about everyone's background here, but I'm going to start very basic to just describe what a nuclear reactor does, and that kind of frames what we are doing. So first you need to produce neutrons, and you need fission, and that creates heat. Reactor physics describe neutron transports, depletion, decay, so how much heat you're generating in a reactor. That's one of our technical areas. That reactor physics is driven by the uranium. That's the fuel used. It's not the only fuel option, but the predominant fuel option. Depending on the form of that uranium oxide as in light water reactors, uranium metal as in a fast reactor cooled with a liquid metal, like the 1 terapower is building in your state here. Then you need to know how that materials perform over time, because you'll see a lot of degradation. Understanding that degradation is important for safety. So that's what we call fuel performance. We develop a code called Bison that captures that behavior. Capturing that behavior means you have models that describe how much does the fuel swell as a function of time, how much does the thermal conductivity degrade. In order to be able to answer those questions, we do supporting simulations that sort of describes the physics happening at the fundamental level, scales that up to dimensions that are at the macroscopic scale. This happens to be a trisoparticle, a particular fuel form. A typical fuel rod is meters long and centimeters wide, so you need to upscale this information to inform fuel performance models. All right, so that's the fuel. And the conductivity is conducted through your fuel, you can have an encasing cladding material, and the next step is for a fluid of some form to transport that heat away. That's why we spend effort on thermal fluid. So that's basically how the water, the liquid metal, the molten salt, or the gas transport the heat away from the fuel elements. That heating or that fluid, heat transfer fluid, goes to heat exchangers. It might go to a direct steam generator to then create what is used in a generator to create electricity. All those things are captured in this technical area. We've said the fluid needs to go through a pipe. There are various engineering components that goes into the system. They're all made out of materials. We don't look at manufacturing of those materials. There are other programs do that. It's an important problem. But we do look at degradation of those components. Today's light water reactors, some of them were built in the 60s. That's reaching 60 years life. They've been extended for even longer. I bet some of these reactors will be around for 100 years before they are fully decommissioned. That's a really long time. Some of these materials are not changed, but they are kept in the reactor for all of that time. If you can, let's say you designed your reactor for 20 years, which I think was roughly the original design life when they were first deployed. If you do an economic calculus, how much return on investment you get for 20 years, and then you can extend that to 80 years, that makes a lot better case for that investment. Of course, you have to continue to invest over time, so it's not for free. But if you can predict how a material behaves and you can design a material that ages really well and lasts for a long time, you win a lot. So that's what we're doing in the structural materials and chemistry technical area. And maybe the most important part of a nuclear reactor is that none of these things happen in isolation. They happen all at the same time, at different time scales, but they do happen all at the same time. So we need to couple this together. We do that in what's called multiphysics. And to help us achieve that, this technical area also developed what's called the MOOS framework. I'm sure many people here have heard about that. It's developed at Idaho National Lab. It's the finite element code development analysis framework that underpins most of the codes you see here. Most of them are built on that framework. That's for MOOS, mostly deployed for advanced reactors. Vera is the same terminology for light water reactors that was developed under a project called CASTLE that was led by Oak Ridge National Laboratory. So that's not a very quick, actually. I spent quite a bit of time on that, but I think it's an important basis, especially for someone who's not familiar with this or super familiar with this topic. We have these technical area, kind of all the different reactor types you hear about, and I list them here. Light water reactor, this is basically defined by what type of coolant you have. So light water, that's what we have mostly today. Gas cooled, it's a helium or potentially some other gas that cools the reactor. Molten salts, high temperature, you melt kind of sodium chloride and you let that, or some similar or different but similar salt, and let that cool your reactor, or a liquid metal. All those different reactor types cross-cut these areas. They share many features, but they are a little different. So you can't just treat a generic reactor. You need to pay attention to the specific aspects of each type. This program, we view our success as not only deploying these tools and then being able to simulate things. We want it to have an impact. So we want our stakeholders, industry, the Nuclear Regulatory Commission, and so on. We want our tools to have an impact on how they do business, meaning we want them to use our tools to do a better job, a faster job, and so on. And the fact that we view this as our key success criteria is why we don't only develop these, we make sure they are maintained, we make sure we have training for the tools. All right. So next I'm going to go through a couple of examples for each type of reactor and type of technical area. I'm going to start with light water reactors. We know a whole lot more about light water reactors and the fuel in light water reactors than we do for the other reactor types. We still have good knowledge about those, but not nearly as much as for light water reactors. So we know these fuels work, but that's not the end of the story. So two problems that face opportunities that face the industry today. So we want more electricity on the grid. The fastest and easiest way to do that with nuclear is to work with our existing fleet, because construction times are still pretty slow. They're not measured in 1 year, they're measured in multiple years. So the best thing we can do is to try to get more electricity out of existing plants. Two ways of doing that is to operate the power, so produce more power in your reactor. That leads to certain new phenomena that you need to understand. In particular, you might boil a little bit more water that interacts with your cladding material. Higher temperature means that the properties of that cladding evolves. By itself, not a problem, but you need to make sure that if you have an accident and you lose your coolant, like what happened in Fukushima, that cladding still stays intact, and that requires material understanding. We spend time on that. Another option is to keep the fuel for a longer time in the reactor. That provides fuel cycle efficiencies and decreases the cost of the fuel, essentially. So this is a picture of a fuel that has been exposed to burn up. You see a lot of cracks and a lot of changing colors. That's just a sign of how your fuel evolves with time. You need to understand what that evolution means for the performance. Again, in the case of an accident, when you lose your coolant, your temperature goes up, and some of the fission gases retained here may either fragment the fuel, get released, and that influences how it interacts with this cladding safety barrier. You can perform tests to understand these, but they're pretty complicated tests. You can't do these in a regular reactor. For once, no utility would allow that experiment in the reactor. It would risk destroying things if it goes wrong, and you couldn't produce electricity at the same time. So by understanding how this connects to various scales of the material, we do provide understanding on its own, but we also enable connecting to experiments that are simpler, that you can perform in a laboratory environment, and that's really valuable. I'm not going to describe all the details here, but this is kind of a summary of the approach, but typically using coupling between length scales. So if that wasn't clear, these are atoms. This is a microstructure, grain size, so this is measured in microns, and this is about a centimeter or so. Again, I'm not going to describe everything on this class. This is more an indication. So I described the problem here. Now we need to break down at various scales what's going on, what phenomena are important. And all the words you see here are different phenomena that are important, that we need to understand and resolve. And this here kind of describes, so this is various microstructure features. This kind of describes in a pellet how that microstructure, where it exists, and how it evolved with time. And these stars here are the key pieces where we see that more information is needed. So maybe that's a good point of explaining actually. So there are some models in the past. There's no need for us to reinvent the wheel. So what's working is working. These stars identify where we think we can make a contribution. So we keep the things that are working well. Don't waste your time. The things that are good, well engineered. Focus your effort on where you can make an impact. And that's what these indicates. And the type of work that we're performing here involves molecular dynamic simulations. You see that here. So this is fuel, uranium oxide. This is a fission gas, so forms when uranium fissions xenon. These bubbles could lead to bad behavior. This is a fragmentation or fracture. You see the grain boundary loses its integrity. That's what happened under this sort of what we call microcracking. It may lead to gas being released. So we perform this type of analysis at the atomic scale. We then look at the grander scale. So this is a bubble like this, and we look as this grows, how they can connect. This is kind of more of a mathematical analysis. We aim to put these pieces together to then have a good model for how this behaves. The alternative is shown here. Here we just have some simple model. We don't care about what actually goes on. We just write if temperature decreases, we release some gas, or we create some fracture. This works if you have data to calibrate it to, but if you change the conditions, like what's your maximum temperature, what's your rate, does this happen in the beginning of the fuel cycle, or does this happen after 2 years? This model would require data for each of those cases to be fully, to be good. With this case, you can get by with fewer data points because you capture the mechanisms. If you have data for one case, the hope is you can cover a much broader set of conditions. Still remains to be proved that we actually can, but that's the thinking. Again, not going to describe all the details here, but these are comparisons how various models are doing. The takeaway from these are, unless you resolve all the important mechanism, you're not going to get the right answer. When this is work in progress, here we show that we actually start connecting all the pieces that I showed on the previous slide. We are not only getting the right answer, we are also getting the right physical behavior. So very promising. So that was the fuel pellet in a light water reactor. The fuel pellet is encased in a metallic cylinder, cladding, we call it. That's there to retain the fission products, essentially. There are more safety barriers, but what the NRC cares about, don't get any radiation to the public. This is actually the fuel pellet is the first barrier. You can't keep all the fission gas in there, but you can keep it in the cladding. You need to understand that that cladding stays intact if you have an event and like a temperature excursion. So this is just a summary of looking at micromechanical mechanisms. So how does creep relate to the microstructure? We have an advanced model that can capture that. This shows us that, yes, we can do that very nicely. In order to run, so this is a cladding, the balloon here is what happens when temperature goes up. In order to be able to do that, we need to capture this behavior in a computationally efficient form. We couldn't solve this for a full-scale fuel pellet. So we formulate the laws here, and then we build machine learning models that capture it at the component scale. We can run those simulations. This is a really, really nice achievement by colleagues of mine at Los Alamos there, where they can reproduce these tests, pink circles, with predicted data without fitting to this. The current model fits to this data point, can do an equally good job. This one just bases on the fundamental laws. And why this is important is, so this is one particular test. These accidents may happen at different rates and for different duration of time. The model we derived will do a much better job extending to those cases. All right, let's move to fast reactors. So fast reactors means that the neutrons in the system have a higher energy. That means you're more exposed to neutron leakage, and there is a stronger coupling between the neutrons and the geometry of your reactor. That can actually be used for safety. So if you have a system and temperature goes up, the mechanical deformation of the material that happens can be used to decrease the neutron reactivity. And decrease that reactivity means that the power of your reactor goes down and kind of shuts itself down. To understand this better, we can couple a code that model, or codes that model heat transfer, codes that model the deformation of the structures, and codes that calculates the power. We do that in a simplistic way today, and that works, and you can design this with fairly large margins. If you have more accurate tools, you can understand it better, define the safety requirements better, and design a better system. So that's the goal here. And it's also a work in progress, but we show here how we can heat conduction. These are these two problems, and we can look at the mechanical deformation. The next step here is to bring in reactor physics. And we can show here that we can do a good representation of that, and I'm going to leave it at that. So that's fast reactors, metal-cooled fast reactors. I mentioned gas-cooled reactors. Gas-cooled reactors use a lot of graphite, both for moderation and as a structural material, so as a dual purpose. It's important to understand how that graphite deforms with time, both because it has a structural role to play. So if it fractures, then that could be a bad thing, or depending on which type of component, it's not such a bad thing. It could change its dimensions. Coolant, like gas, flows through an opening where the graphite is. If that gap closes, you're not going to have the engineering functionality you want. You need to design so that doesn't happen. That means you need to understand how your material changes with time. So we develop models that can do all of those things, and we're providing these to developers of gas-cooled reactors and fluoride-cooled high-temperature reactors. That's, if you heard about Kairos Power there, they have a kind of a gas reactor design looking like a gas reactor, but they have a molten salt for heat removal instead. It's a very neat design. So that's graphite. I'm not gonna spend more time on that because we have a lot to go through. Molten salt is another option. That's unique because in a molten salt reactor, you do not have your fuel in a little pellet or enclosed in a cladding. Rather, the salt is dissolved in the actual molten salt. So the fissionable material is dissolved in the actual molten salt. So if this is an extremely simplified picture of a reactor, the salt flows through this loop. And you need to understand what that flowing fuel does. When you decay products, they impact reactivity. All those things need to be tracked. You need to track the fission product. In this case, they can deposit at various parts of your reactor. Molten salts can be corrosive, so you need to understand how much corrosion you have to understand how long your reactor can be run. So a lot of the work here is focused on chemistry and fluid flow. We develop tools that can resolve the flow, the heat transfer, the corrosion, and the deposition of fission products, as well as how that couples to neutron reactivity. This is a picture of how all those codes are coupled together. Again, the details don't matter. In this particular case, we're working pretty closely with the NRC to get them a tool that they can use when applications comes into the Nuclear Regulatory Commission, so they can analyze the safety of the systems proposed by industry developers. There is also work. I said chemistry is important here, and that is just because the chemistry of the salt evolves so much. You need to make sure that the redox behavior is in the range that is defined for the reactor. To do that, we need to couple to knowledge about how the chemistry evolves with the composition of the salts. Not only the chemistry, but properties can change. We do that by coupling to databases. We call them MSTDB, TC, and TP. You can look at an Oak Ridge website to learn more about that. In order to couple this to these fluid simulations, we need an interface with a thermochemical software that can be connected to the fluid flow codes. Some of those connections are kind of computationally slow. That's again why we use machine learning models to speed up the workflow. The last reactor type I wanted to cover is microreactors, and as you probably know, but as the name indicates, micro means that this reactor is much smaller than a big power plant as we see them or as they are big power plant like a light water reactor today. You need to design them kind of smart. One way of doing this is using solid moderators, yttrium hydride here. The height and compactness of these means that the multi-physics aspects are really important, so we need to couple neutronics with heat conduction, solid mechanics. Not different from the other reactors, but it's even more important. Some of these reactors also use heat pipes, technology that was actually invented at Los Alamos many years ago. It's used in electronics today, many applications. You can use them for reactors. Takes the heat out really effectively in small geometries. So this is just a statement. Yes, we can model this. We can use our tools to put this together, and we can compare pretty nicely to experimental data. All right, so that's my overview of what the program does, and I probably spent, as predicted, I spent more time on that than ideal for the second half of my talk. But we're going to have time to cover a few nice examples on multi-scale simulation for nuclear fuel performance. And I did already mention some of these things. And let me provide the justification here. So in a nuclear reactor system, I talked about the need to build this quickly, design them, and optimize them. The hardest part, okay, I'm a fuels person, so I'm biased, but the hardest part is the fuel, because the fuel is what powers it. It's what sees the most irradiation. Without the fuel, you don't get any power. And if you want to test it, there's a pretty long timeline to do that. So people are looking at ways of accelerating that process. This picture is taken from a paper that you can find on the NRC's website, defining the concept of accelerated fuel qualification. In itself, nothing new. It essentially tells us, with modern tools and experiments and modern tools and simulation, how can we get from the starting point to the finish point in terms of regulation quicker, and very importantly, while maintaining the same safety as we expect today. The answer is not anything really complicated in the sense that this is just using the best tools you have available, putting them together, analyzing your information in the data in an efficient way. So there's no magic. It's all the same things we've always been doing, but with better tools and more resolution. So I personally came at this being educated in atomic scale simulation. So again, maybe I'm biased, but I think those have a really important role to play here. The reason is that it's really hard to figure out how a material behaves in a non-equilibrium condition. Under irradiation, you create defects. You can do some experiments, but it's really hard to disentangle everything that goes on. In a computer, you can set up your simulation, probe a specific physics. It may not tell you how everything couples, but it tells you how that particular physics piece behaved. From there, you can then build up and try to learn about the coupling. So in materials, when you create a lot of the evolution of properties and how a fuel behaves is related to point defects. So that means a vacant lattice site. A vacant lattice site can diffuse. That determines how fast the fission gas moves out of the fuel. It determines how fast the fuel, or it's one of the physics governing how fast the fuel deforms by creep at high temperature. And I'm going to quickly step through how we can use knowledge on the atomic scale shown here to sort of infer behavior of advanced properties like creep and how that feeds into the thoughts I presented on accelerating qualification. If you didn't have irradiation, this problem wouldn't be very hard. You can determine the thermodynamics of your system. You can, through equilibrium thermodynamics, say how many defects you have and what that does for your behavior. When you drive your system, you need to understand how the damage rates couples to the annealing of that damage, so how fast it heals, and how it couples to thermodynamics. We use that by coupling to something called cluster dynamics, and we use a particular code called centipede. There's a number of equations. They are solved. They're essentially chemical rate equations. We solve those and predict how the material behaves. Again, I'm not going to describe any of the physics here. The important part is that we're able to do that in a way that reasonably represents experiments. These lines here compared to these dots. However, it doesn't do it perfectly. No simulation would ever do it perfectly because we can't capture everything. And even if we captured everything, we couldn't capture it with perfect accuracy. And even if we could capture it with perfect accuracy, these experiments would have error bars on it. But if you want to predict, say something about qualification or how this behaves, we need to somehow capture the uncertainty, or to what degree that we trust our predictions. And by the way, by changing one parameter here in our model, we can easily reproduce those experiments. So I say that we do good enough to continue this exercise and deploy these tools. We also identify a need to sort of use the limited experimental data that we have in a smart way to make our model better. Okay, so, oops. So why do we'll come back to that. So why do we want to do that? Now, we had data for your standard fuel. We didn't really need to go through that exercise. We already knew the answer. But even for light water reactors for UO2, people are changing the fuels. They're putting dopants in to get better performance, in particular larger grain size. Now, that dopant could affect properties. And with the models that we're developing, we can make a statement on adding that dopant, how much does it change properties. And we have shown that. We have shown that by doing so, you can actually reproduce better experimental data taking for these advanced fuels than a model that doesn't go through all the sophisticated steps that we did. I mentioned uncertainty. So something we're doing today for all the types of fuel we're simulating is applying uncertainty quantification that typically embeds machine learning models to be able to evaluate your advanced performance models quicker, because uncertainty means you have to range a large number of parameter sets, that could be 100 of them, and you need to do that quick enough to collect statistics. So we do that, and in the end, you can end up with prediction that has an error band on it, and you can, where you have data, that error band will be small. Extrapolations here, that grows, but we have it in a quantified way. So we don't only say, this is the value that you're going to get. This is the value you're going to get with a certain confidence. That's really important for making decisions. Again, not going to cover any of the details. Also quickly wanted to say, I also mentioned doped UO2. The real reason why you dope UO2 is that during the manufacturing, your grain size increases. That has benefits. And one of them, one of the benefits is better mechanical properties. The fuel is a little softer. That matters because when it hits the cladding, pushes against the cladding, the fuel doesn't push quite as hard because it deforms a little bit itself. That matters if you were to have an accident, and it helps provide more margin for the breach of the cladding. However, in order to take advantage of that, you need a model that can quantify how much does it creep, how much less does it push. And it turns, so for diffusional creep, turns out if you go through the literature, there's still a debate whether this is Nabarro-Herring creep or Coble creep. That essentially means Nabarro-Herring is diffusion goes through, if this is a grain, diffusion goes through the middle of your grain, through the bulk, or it goes through the grain boundaries. And that matters because the grain size for the first one scales with a square and with a cube. So if you made your grain a lot larger, let's say you that by a factor of 10 larger, whether that creep rate scales with the cube or square or the cube, that's going to give you a different result. So we built, using the kind of defect tools that I showed, a workflow that can assess that. And that workflow can eventually be put into a few performance code. I'm not going to show you any of how that workflow functions, but we're happy to answer questions on that later. This is just valid. What we get at the end actually does a remarkably good job describing the behavior of the materials as established in experiments. However, it's very clear that it is Coble creep, grain boundary creep, because this is the prediction for that mechanism. This is the prediction for the bulk mechanism, several order of magnitudes of. That it's a very clear-cut conclusion, and a large set of data can be successfully described. Again, we go through uncertainty quantification. As good as the model is, and we do that from only what we call first principles, so we don't directly involve experiments. It would be not a good approach to throw away experimental data when you have them. So by picking some of that data and improving the model through these uncertainty quantification frameworks, we can get a model that reduces the uncertainty from these big bars here to these small margin, smaller bands here. And this just shows that for a number of different conditions and data points. The original model are let's see if I get that right, yeah. The red points here, and this is the parity plot, so predicted versus experiments. Not too bad, but they're off. The perfect result here is the diagonal line. When we do the uncertainty quantification and Bayesian calibration, we can get a much better result, and we can get those results with a predicted uncertainty, which again is important for answering qualification questions. What I showed so far actually did not involve irradiation. It was just a thermal effect. That's not sufficient, but I'm only going to show one slide on this. So this is irradiation creep. These are experimental data points. This is important at lower temperature. At high temperature, everything in NEALS, irradiation effects aren't that big, but at low temperature, this is important. By using the centipede cluster dynamics tool and coupling that to grain boundaries, we can capture all the physics here and make a prediction for what irradiation creep should look like. The agreement here is very, very good. That was achieved by allowing one parameter to change, but nevertheless, this really captures the relevant physics. And interestingly, while in the bulk, creep is all dominated by, or in thermal equilibrium, creep is all dominated by vacancies, the creation of defects on irradiation means that irradiation creep due to interstitials at grain boundaries is what explains this. So the final step of this exercise is to capture these models in an efficient way that you can evaluate at this component scales for a fuel pellet in a fuel performance simulation. We use neural networks to describe that. This describes how what the neural network looks like, and they say a few specifics here. Again, we're not going to go into details there. This qualifies how well it performs across some parameter space. And the next slide here shows us how that model performs in a simulation of a fuel in a reactor-relevant environment, including during a LOCA test. In the interest of time, I'm not going to go through exactly what the comparison looks like, but even this somewhat preliminary model that were based on the mechanisms, it produced as good of a job as the empirical model or better. The last quick example I'm going to go through is for a completely different fuel. This is for uranium nitride. Uranium nitride has benefits to UO2. It is kind of an electric conductor, so it conducts heat much better. It has the same high melting temperature, or almost as high melting temperature as UO2, which is beneficial. Metal fuels are really good for thermal conductivity, but they swell a lot, so they change the geometrical form a lot. That can be engineered around. Nitrides don't swell as much, at least if you operate them under the right condition. So this exercise goes through defining the same kind of models that I described for UO2. And the problem we want to solve is, at what temperature and radiation condition do you need to keep this fuel to avoid swelling increasing almost exponentially? So that's expressed by this point here. This is swelling versus temperature, similar things as burn-up. If you go above a certain temperature, the slope of this line, which means the swelling rate goes up a lot, and that's not great. So we want to understand how that inflection point depends on temperature, irradiation conditions, and so on. This is the same kind of concept that I've already described several times, starting with low scales, understanding or defining parameters, identifying the relevant physics, coupling all of that at a large-scale model, connecting to experiment where it makes sense, use machine learning to optimize this, and then say something about performance. So this is a validation step again. There are separate effects kind of tests. You look at some diffusion behavior, experimental data compared to predictions as function of chemical conditions and which species contributes to it. All that matters here is these points are fairly close to the predicted line. So we have enough confidence that we're doing a decent job. As you see here, decent job, not a perfect job. And if you look at this swelling behavior, so this is swelling as function of swelling and fission gas release as function of temperature for different power densities and burn-ups. And again, if you compare this yellow line with the experimental data, we actually capture this behavior pretty nicely. The different curves here represent different populations of gaseous elements. So that means, are they in the bulk? Do they interact with grain boundaries? Or do they interact with dislocations? Where these bubbles are really drives the behavior. Turns out that dislocation bubbles is really important. And let's see, I think I have. These, the kink you see here, that happens, that it's simply connected to the transition from irradiation-driven diffusion to thermal diffusion. So not a very complicated explanation, but it hadn't been identified, and that is what controls it. So as long as you avoid the high temperature regime where diffusion just gets faster due to thermally created defects, this fuel doesn't swell too much. And this is my second to last slide. This just summarizes the next step we're taking here. And this is the framework we have for uranium and nitride swelling. These are the predictions you saw, and these are the uncertainties. These uncertainties have now been reduced compared to original or they've been quantified and reduced by doing the same Bayesian calibration exercise that we showed for creep in UO2. There are experiments underway. Roadrunner is the name of them, together with Westinghouse and Oak Ridge, where we try to do new measurements to provide data points that can be used for uncertainty reduction. So that I covered all of it. It was probably a lot to absorb. That's why we have Q&A here at the end. I hope I was able to give you an introduction to the NEAMS program and what our view of modeling and simulation and how that can be helpful to the nuclear energy community. We'll get to that actually at the last bullet. I also gave you some examples on fuel performance and accelerated qualification for uranium oxide and nitride. I emphasized throughout this, I think, the concept of multi-scale modeling, and I did mention how AI and ML allows us to perhaps accomplish the goals that we set out a number of years ago with multi-scale modeling. So it really enables us to connect to experiments and the engineering component scale simulations in a way that we can have a real impact on development, licensing, and deployment. And I think there are lots of topics here that are interesting for students to learn about and to perform research about, and maybe even take a step into some of these fields and contribute to the nuclear fuel and nuclear reactor and nuclear energy field. So with that, thank you very much for listening, and I'm happy to take questions.
On one of your slides, you mentioned ion beam experiments. I was wondering if you could comment more on that, what that achieves.
Time and efficiency. So ion beams can, in order to reach a certain burn up, you need to keep the reactor maybe for 3 years. With an ion beam, you can accomplish the same amount of damage in days. The challenge is the damage rate is much higher, and they're not necessarily the same as for a neutron. So you need to spend time to understand how you do the mapping from those ion beam conditions to the neutron conditions. If you can do that, the ion beams offer a path to do a rapid experiment that can provide some information that helps the model development, but it has to be done in a careful way. Does that answer the question? Okay, good.
Hold on, John. I'm going to give you the mic.
That way they can hear you online.
Cool. First off, thanks for being here. Appreciate it. Curious in particular with high temperature gas reactors and TRISO fuel, are you incorporating, operational data from places like Fort St. Vrain in your modeling, and is that?
We do not incorporate data from Fort St. Vrain, which is not too far away from here. We do incorporate data from the latest advanced gas reactor fuel testing program. Those irradiations were done at Idaho National Lab at Advanced Test Reactor. I honestly don't know if we have enough. I don't know the answer why we're not looking at. Typically, if there is an old reactor, we try to simulate that. I don't know why we're not looking at that one. It could be that there hasn't been enough characterization afterwards, so it's not 100% clear what would we be comparing to. But it's a good question. If it was characterized, it would provide a very valuable data set. But to the best of my knowledge, we're not using any data from it.
We have another question in the back.
Yeah, great. Thank you, David. So my question is, in NEAMS today, if you have to pick the top one or two bottleneck, which is limiting the predictive fuel behavior. So what would you pick? Is that like the fission gas, the fracture, or the coupling between different mechanisms that you mentioned?
So the two most important, it depends a little bit on what type of fuel we're talking about, but generally speaking, fission gas and thermal conductivity are the two parameters that are most important on the eventual fuel behavior. For metal fuel, there is also chemical evolution, so interaction between fuel and the chemistry. Fission gas is still at the top of those, as which one is most important. The bottleneck there is understanding, being able to make predictions where we don't have any data. You see me making bold claims, we can extrapolate this. And I do have some belief in that, but how far can you extrapolate it? And at what time does new physics appear? The case in point on high burn-up UO2 is one, where suddenly your microstructure changes and your property changes. Would we have been able to predict that without the experimental knowledge? Honestly, no. So that's a bottleneck. Can we in the future take that to the next step where we kind of can predict something without having at least some form of template provided by testing data? I should emphasize, never would I advocate for modeling and simulation alone. You have to work close integration with experiments. It's absolutely critical. Whatever your field of study is, it doesn't change. But still, optimizing the route to get to that answer, that is a bottleneck. So that is fission gas. I think triso fuel is used by a lot of vendors today. As we push those to higher powers and higher burnups, I think the coupling between these layers and chemistry and various failure mechanism, being able to understand those failure mechanisms at higher or more extreme conditions is another bottleneck. Both of these points to another bottleneck. I think we need to do a better job integrating experiment. As many examples as I had of this, they're mostly historical examples. We should design the experiments at the same time as doing the modeling and have those interchange data at a much more rapid pace than we typically do. So that would actually be my biggest bottleneck. We need to do that circle in a much more efficient way to be able to answer the questions we're trying to answer in a timely manner. That might have been 2 or 3 points. I'm not really sure what I gave you.
You do not have, I really appreciate it for you sharing those insights. So actually, I want to, ask a slightly different questions here, just as a continuation of the discussion this morning. So, and this question is more for our students. So in NEAMS, right, is focusing a lot on, it's not all, but a lot heavily on code implementation testing, right? And then later on, use it. So in the age of AI, seeing the capabilities of like cloud code or codecs, right? What perspective that you would like to share to our students, right? As a student now, later on, who might be going into a next job, like working with NEAMS or other softwares, right? So what would you like to share?
Very good question. I think I'll have 2 perspectives. So there is an opportunity, the very advanced answer here, or opportunity, is where you have AI agents sort of performing all the workflows that I show and learning about predictions on the way and making decisions and helping with design reactors and materials. I think you're going to see, if you heard about the Genesis projects, it's DOE initiatives to kind of push those boundaries in the science, research, development, and science domain. You're going to see some of that. That's like the grand challenge. What I want to see in the NEAMS program is people adopting tools to do what they are doing more efficiently and better. So that could be analyzing your data better, connecting making that connection between experiments and modeling quicker, but also if you have a microstructure picture, you can try to go in and analyze that and connect to modeling. That's pretty hard. It takes a lot of human labor. We can automate that. You can incorporate that in our work much better. Code development, we are developing agents that help you run a MOOS simulation and potentially write code. So that would not only make it more efficient, but it would also, for like students and other users coming in, you wouldn't have to spend as much time in training. You could get down to the problem quicker. And what I said about uncertainty quantification, I think that's is that really an innovation? It's not, because people have been doing statistics for a long time for data analysis. But what machine learning and artificial intelligence enables us to do is it much quicker. So it can be a natural part of our workflow that a person who's a materials expert can do. You don't need an applied mathematician to do it. So it's a long-winded way of saying adopt it, use it to make your work more efficient. But don't forget about learning the physics or understanding the physics, because crap in, crap out. You need to be able to identify when you get a poor answer. We're not at a stage where AI is trustworthy enough to get rid of us. So yeah, use it where it makes sense, but apply your common sense and your understanding of science and engineering to make good decisions.
Well, thank you, David. Thanks for joining us today. I thought you did a great job with your talk.